Hello 171 class, this is your notes for section 2.6 part 2. We're going to move our way from vertical asymptotes to horizontal asymptotes. So if you remember, a vertical asymptote was a vertical line that the function headed towards infinity on either side of that line as we made our way closer and closer to that number. A horizontal asymptote is similar, but it's on the left or right side of the graph. As we make our way to the, in this case, the right-hand side, this function gets closer and closer and closer to some number that we're calling b. So as x makes its way to infinity, the function values makes its way to b. Or again, what you'll say in calculus, the limit as x goes to infinity is b. Right? It's getting higher and higher and higher, but it's never going to get to b. All right, and then the same thing, likewise, but this one's coming downhill. As we make our way to infinity, we're headed towards b. Alright, now, it doesn't show an example here. It says or decreases. It could be the other way around, that we're making our way to the left-hand side of the graph. Alright, I just did a mirror image of that first graph, but if we make our way to the left side and we're approaching a number, that could still be a horizontal asymptote. So I don't want to confuse you to make you think that it has to be going towards the right side of the graph for there to be a horizontal asymptote, left or right. If we're approaching a value, if we're settling in on a specific number as we make our way to the right or left of the graph, then that is a horizontal asymptote. Okay, now thing here, you can cross a horizontal asymptote. Notice we crossed it right here, then we came back up towards it. So you can cross a horizontal asymptote. You cannot ever cross a vertical asymptote, but you can cross a horizontal. Alright, in trig, you'll see a function where you actually cross a horizontal asymptote an infinite number of times. You just keep crossing it. But here, it'll be common to see a horizontal asymptote, a graph that we cross one time, and then we just start growing up towards it or coming down above it after we've crossed it. Alright, so again, here's another visual to what it means to be approaching a number. So this graph, g of x equals 4x squared, there's a polynomial on the top, divided by 2x squared plus 1, a polynomial on the bottom. When we divide these, we get no vertical asymptote. We don't see any place where it breaks apart like the last video, because we can't, this bottom can't be equal to 0. Alright, so we don't get a vertical asymptote, but we do get a horizontal asymptote. As we make our way to the left, the function values get closer and closer and closer to 2. And as we make our way to the right, the function values get closer and closer and closer to 2. So what do I mean by it's approaching 2? I mean, like when I plug in this first example, I'm plugging in a number between 3 and 4, so somewhere around right here. We're getting really close to 2. We're not quite to 2 yet, okay? The function values, the outputs, are getting really close to 2, but they're not quite 2, right? And this stops at 5. If I pick up from 6 on the table and just keep my way going down, bigger and bigger numbers, that means I'm making my way to the right on the x-axis towards infinity. The function values get closer and closer and closer to 2. That's what we mean by it approaches 2. Alright, so notice again that definition. As x approaches infinity, as we make our way to the right side of the graph or left, the function values, the y values, are getting closer to just a single number. Alright, again, that's what we see right here. We're getting closer and closer and closer to 2. Alright, how do I find a horizontal asymptote? So this is some rational function, okay? Polynomial on the top, polynomial on the bottom. And notice the a's are what we're using for coefficients here. B's are what we're using for coefficients here. And notice a sub n is the leading coefficient on the top, n's the degree, and b sub n is the leading coefficient on the bottom, m is the degree. So a sub n is the leading coefficient on the top, LC leading coefficient, b sub m is the leading coefficient on the bottom. Alright, if the degree of the top, right, is smaller than the degree of the bottom, alright, like degree 3, degree 2, degree 2, degree 3, degree 5, degree 6, then y equals 0 or the x-axis is the horizontal asymptote, meaning the graph will get closer and closer and closer to the x-axis on the left and right side. If they're equal, if the degree here and the degree here are the same, if it's degree 5, degree 5, degree 2, degree 2, then the line y equals a sub n over b sub n, the leading coefficient in the numerator divided by the leading coefficient in the denominator, is the horizontal asymptote. Now we will reduce this, right, no matter what a sub n and b sub n are. The leading coefficient at the top, leading coefficient at the bottom, reduced. Alright, so if it's like 4 over 2, don't leave it. Simplify it. If it's 2 over 3, that's simplified. If it's 4 over 6, that's not. We would reduce it to 2 over 3. So we always reduce that, no matter what those two numbers are. And then if the top is a bigger degree than the bottom, then there is no horizontal asymptote. Okay, it's not going to settle down to a single number. So in this example, notice 2x squared plus 1 is the denominator each time. But the power on this 4x goes from 1 to 2 to 3. So right now, the denominator's got the biggest power. So the degree of the denominator is 2, the degree of the numerator is 1. That's the first scenario. So y equals 0 over the x-axis is our horizontal asymptote. The graph makes its way down to the x-axis on the left and right side. Okay, but here, degree 2, the degrees are equal. So the line y equals the leading coefficient on the top divided by the leading coefficient on the bottom, y equals 2, is our asymptote, a horizontal asymptote. So as this graph makes its way to the right side, the heights get closer and closer and closer to 2. Alright, notice that's the function that we did in the last problem. 4x squared, 2x squared plus 1. So that is this function. So we know that it is approaching 2 on the left and right side. And then this last one, 3 is now bigger than 2. The degree on the top is bigger than the degree on the bottom. So there is no horizontal asymptote. So this function kind of bends funky in the middle here, but it doesn't settle down towards a number. It keeps getting higher on the right, lower on the left, and then again, it doesn't have to be that way. It could be, a graph that looks like this. That doesn't have horizontal asymptotes either. So as long as it doesn't settle down towards a number on the left or right side of the graph, then there's no horizontal asymptotes. Alright, so let's take the last big thing that we do in this chapter is to graph these things. And when we graph them, we want intercepts. We want to know where it crosses the x-axis, where it crosses the y-axis. Any vertical asymptotes or holes in the graph, and then the horizontal asymptotes. Put all that together, and you should be able to give a pretty good graph. Along with using, remember, f of x is the same thing as y. Using your y equals screen on your calculator and literally graphing this thing and seeing what it looks like to help you. Alright, so x-intercepts. X-intercepts mean the top equal to 0. So if I take 2x minus 1 and I set that equal to 0, add 1, I get 2x equals 1. Divide by 2, I get x equals a half. So the x-intercept is 1/2. Now you always check with the denominator to make sure that that's not a domain restriction. So x equals a half. 1/2 minus 1 is negative half. That's not 0. So that means that that's fine. So 1/2 is where we're going to cross the x-axis. Alright, the y-intercept, let me switch colors. The y-intercept is always f of 0, again for any of these types of functions. So if I plug in 0, I get 2 times 0 is 0, negative 1. 0 minus 1 is negative 1. I get negative 1 over negative 1. Negative divided by negative is a positive 1. So 1 is the y-intercept. Okay, f of 0 is always the y-intercept. Alright, vertical asymptote, I'll switch to black to do that. You try to factor 2x minus 1 and x minus 1. I would try to factor this, okay, but it won't factor. So you take the denominator as it is and set it equal to 0. Alright, you try to factor and reduce, but since it won't factor and it won't reduce to begin with, then it won't reduce now. So x equals 1 is a vertical asymptote. So there's my vertical asymptote. I'm going to dash it. Alright, there are no holes in this graph because there's nothing that canceled here. Okay, so no holes, but there is a vertical asymptote because the denominator still could be 0. Even though I couldn't factor it, it still could be 0. So that domain restriction there, 1, is a vertical asymptote in this case. Alright, then the horizontal asymptote. This is degree 1 on the top. This is degree 1. So for number 4, I'll do it in green. Number 4, the horizontal asymptote is y equals, it's the same degree, leading coefficient top, leading coefficient bottom. Y equals 2 is my horizontal asymptote. Alright, so I'm going to come in here to 2, make that horizontal dashed line. Alright, and there's that's that big things that I want to make sure I have illustrated on the graph. Okay, I have the horizontal asymptote y equals 2. I have the vertical asymptote x equals 1. I have my x-intercept, I have my y-intercept. So now I'm ready to graph the function. Now, it's going to do like this. It's going to bend from this asymptote down and hug that, and then it's going to kind of flip up here. But if you don't know that, and it's fine to not know that until you get a handle of these, graph it. Alright, plug it into your calculator. Remember, f of x is the same as y, so y equals, click y equals, type in the top and bottom. You need parentheses, top and bottom, when there's addition or subtraction in there. Hit zoom 6 to make sure I'm in the right window. Alright, and then there's what I see. There's that. Again, that's not part of there. That's the vertical asymptote. Okay, so this graph bends down below that line y equals 2, and then it bends from above and comes down to touch it. So this graph is going to look like this roughly. Again, it's fine to press the trace button, and you can move around here. You can plot some points to make it a little more accurate, like -2 roughly 1.7, so -2 roughly 1.7, but you don't have to. I mean, it's just a sketch, and typically a lot of these problems that you'll do in your homework are going to match the graph anyway. So just remember, when you go to match the graphs, parentheses around the top, parentheses around the bottom. Okay, if they give you a window, multiple choices give you a specific window, press the window button and match up the window, and then you can match the graphs. But otherwise, you're just sketching it anyway, so it doesn't have to be perfect heights. You just have to kind of get the general idea. But these are the things that you're going to want to know how to be able to find. The x-intercepts, y-intercepts, and then any asymptotes the graph might have. Alright, so this is something called a slant asymptote. If you ever see a graph, again, this is a vertical asymptote right here, so it's actually not there. But if you ever see a graph that is going along on a straight line, and then it turns and hits a vertical asymptote, and then it comes back down, but then it starts right back on that straight line again. So the line I see here looks about like that. So this line right here, the blue line that I graphed, is what we call a slant asymptote, and it literally is a linear equation. It's going to have the look of y equals mx plus b, like a line that you've probably seen that form of a line before. If we graph that line right here, the y values for this line get really close to the y values for this rational functions graph. As we make our way towards infinity or negative infinity, they start to be virtually the same. And that's what we mean by a slant asymptote. It's a little linear equation that's not vertical or horizontal, but the graph makes its way towards that on the left and right end. Okay, definitely not necessarily in the middle, especially where the vertical asymptote takes place, but on the ends it'll make its way to that. Now the way we find the equation of a slant asymptote, the way I would find the equation of this blue line is just to do long division. So this is and this will only occur, slant asymptotes will only occur if the degree of the top is exactly 1 higher than the degree of the bottom. So if I'm going to do long division here, I got an x squared. Remember, there's no x term, so I need to account for that. 0x plus 1. and then an x minus 1 on the outside. Alright, what do I multiply x by to get x squared? I multiply by x, so I'm going to put that straight over top of this x. And then multiply x times x is x squared. X times negative 1 is negative x. Alright, and then subtract, change your signs. Add, I get a positive 1x. Bring down your remainder. The next term. X will go into x, or what do I multiply x by to get x? Positive 1, so plus 1. And then multiply here, I get x minus 1. Change my signs. Alright, I get a remainder of 2. So technically this is equal to x plus 1 plus, because that's a positive, 2 over x minus 1. Alright, that's what this is equal to. But for the purposes of the slant asymptote, it's just the quotient. Okay, it's only this part. Okay, we don't include the remainder. Okay, it's like it's not even there. So this slant asymptote is y equals x plus 1. Alright, so there's the x squared plus 1, x minus 1 on the bottom. Graph that. There's my graph that we see here. If I go back in and I put in y2, the equation that I got for the slant asymptote, y equals x plus 1. And don't forget to put the y equals. Alright, on a paper test like your final exam, if you leave off the y equals, it's not a line anymore. You got to have the y equals to make this a line. When I graph it now, there's that y equals x plus 1 that goes through there. Remember, mx plus b, m is the slope, b is the y-intercept. The y-intercept is 1. And you can see right there it's crossing. There's 1. It's crossing right there. And it has that slope of 1 there, positive 1. So, slant asymptotes, when you see that, find the slant asymptote. Just remember long division. And then definitely don't forget to leave off the remainder. If you don't leave off the remainder, let me just show you what happens. If I include the remainder plus 2 divided by parentheses x minus 1. If I leave the remainder there, go back here and make this a bold line so you can see. There's the original function, the x squared plus 1, and now here's the other one. If you don't leave off the remainder, it's going to be the exact same function again. Okay, they are equal. This is equal to this if I don't leave off the remainder. But leaving off the remainder, now it becomes that line. This asymptote place in here doesn't take place, and I get the line. So got to make sure that when you do this, you only put in the quotient part and leave off the remainder. Alright, now let's do a word problem that has to do with this stuff. These rational functions. So a commuter drove to work. This was his distance. So this is 40 miles down here, our little picture. Alright, and returned again on the same route. His average speed on the return trip was 30 miles per hour faster than his outgoing trip. Okay, he didn't want to go to work, he wanted to get home. Express the total time required to complete the trip as a function of the average velocity on the outgoing trip x. Alright, so remember, distance equals rate times time. That's what we're dealing with here. Distance equals rate times time. The distances are equal. Okay, they're both 40 miles. So I'm going to go in here and change this to a 40. Alright, he drove 40 miles, returned the same route, so he returned 40 miles. The average velocity on the return trip was 30 miles per hour faster. Now, they want average velocity outgoing trip, this distance, or this 40 miles, to be the one that uses x. So, average velocity, that's the r. So this is telling us to use x for the outgoing r. Alright, so there's 40 equals x times t. On the way back, they tell us that he was going 30 miles per hour faster. So 40 equals x plus 30. Alright, if x is how fast he's going to work, then x plus 30 is how fast he's going home from work. All right, now I'm leaving the t's there, even though the t's wouldn't actually be equal. Let's do t1 and t2. Okay, because obviously if it's going faster, this would be smaller. But the time required to complete the trip, t, the total time, is the sum of these two. All right, so what we're going to do is we're going to solve for t1 and t2. So t1, if I divide both sides by x, I get t1 equals 40 over x, and that's the time it took him to go to work. If I divide both sides by x plus 30, I'll get t2 equals 40 divided by x plus 30, and that's the time it takes him to get back home from work. And then if I add t1 and t2 together, I get the total time it took him to go home from work. So I would get t equals t1 is 40 over x, and plus t2 is 40 over x plus 30. Alright, and then there is my function that gives me the time required to make this trip, depending on what that initial speed going to work was. Alright, 40 plus 30, 70. No, if that was it, then we could figure it out. But it just depends on what the original x was, and that's what this function is designed to do.